Okay, good morning. Let's start the morning session. First speaker is Sebastian, please.
All right. Thank you so much. Good morning, everyone. So today we're going to continue with the discussion of divergences. Let me remind you what we've done in the last lecture. In the last lecture, we really scratched the surface of the discussion of infrared divergences. We learned a little bit about how they govern the long-range dynamics of systems, and in certain cases, like in QED or in scalar QED, you can understand divergences as exponentiating, and as a consequence of the Bloch-Nozick theorem that we discussed, also the inclusive cross-sections are finite. So, as I said, this is really just scratching the surface, just to give you some intuition about what infrared divergences are, that they're not really that scary. We really don't have time to go into a lot of details in other theories, but if you have any questions, feel free to come and ask me later on, and I will be very happy to either discuss or give you some references on this topic, which is very fascinating. What we're going to do today is we're going to move on to the discussion of UV divergences or ultraviolet divergences, and we're really going to follow a very similar path. First of all, we're going to discuss what are the divergences, and then we're going to move on to an explicit example in which we can understand what's going on. And once again, the story is going to be very similar. Divergences will be associated with the breakdown of a basic assumption that we make when we study perturbation theory, and is the assumption that the structure constants or coupling constants are constant. And then we're going to revise this assumption and see how this actually rescues the problem. All right, so I'm going to start with the topic of just asking what are the ultraviolet divergences, or UV. I believe probably most of you know the answer to this question from your courses on quantum field theory, particle physics. So let's start from a basic power counting. Okay, what I'm going to write down is a schematic form of a Feynman integral. Okay, so let's say we have loop integration in d space-time dimensions. Okay, I'm going to call capital L the number of loops. D is the space-time dimension, lowercase l is are the integration variables. And then the average integral looks like this. There's some numerator that comes from a contraction of the vertices and really the matter content of your theory. And then downstairs, we have our propagators. Okay, so in my notation, I will be calling the number of propagators, which is really the number of internal edges of your Feynman diagram, capital E. So E is going to be the number of propagators. Okay, and then Q is the momentum going from through every edge. So each Q, after you solve for momentum conservation, is going to be linear in the L. So that means that each propagator or inverse propagator is really quadratic in L. Okay, so then what we can do next, this is the simple exercise. What you can do is you can take every single loop momentum LA, and then we can rescale it with some parameter. Let me just call it X, with some L hat. So I'm going to uniformly rescale F1, and then take X to be very, very large. Okay, so what's going to happen here is that, let me just look at schematically how the X dependency is going to look like. Well, first of all, one of the integration variables we're going to trade for X. And then we can count how many powers we have, right? So upstairs we have d times L just from the measure. And then downstairs we have, well, each of these is quadratic and there's e of them. So the power counting is minus 2e. And also let's not forget that there was some numerator in principle. So let me just call the degree of the numerator in L as d sub L, d sub n. Okay, that's actually, strictly speaking, this formula is not correct yet. And that's because there's supposed to be a -1 here. Okay, this -1 comes from the fact that I've actually counted one of the x's in here. So for example, what you can do is you can, to understand this -1, is that you can select one of the components of the loop momenta as your victim. So let's say this one. And this one you're going to trade as dx times L1, 0. Okay, so this one, dx is soaked up in here. And then for the other ones, dL mu A, you can write this measure with the hat. Okay, so this is the reason for the offset of the one in here. Okay, so this tells us that in our integration, really the overall scaling of this integral is going to look like this. And what we would like to do is integrate this all the way to infinity. So all the way to infinity because we're interested in the UV or high energy. But really, so what you can see straight away is that if this exponent is too large, then this is just going to blow up. So what we need to do is we really need to regularize our integral. And as we discussed last time, there's actually many ways of regularizing integrals. So some common approaches are dimreg, which is in fact the most common of dimensional regularization. There's probably Villars and other approaches. But for the purpose of this lecture, what I'm going to do is just impose a hard cutoff. So hard cutoff I'm going to call lambda. So lambda is some scale that is the UV cutoff in our theory. Well, but notice that x is actually dimensionless because I just pulled it out here. So it's some dimensionless number, and lambda has dimensions, mass dimension 1. So in fact, what I'm really supposed to be doing here is dividing lambda by some momentum relevant to the problem, just to make the cutoff dimensionless. Okay, so let me emphasize this thing here is the UV cutoff. So I hope this is very familiar to all of you. So now let me, how many of you have seen this before? Yeah, okay, good. So now let me talk about the superficial degree of divergence. Which is just characterizing how fast this integral can diverge. Okay, so let me call it d, lowercase d, and I'm going to define it as this quantity here, dl minus 2e plus dn. Okay, and now you can study what happens depending on the sign of d. All right, so let's classify that. If d, there's going to be three cases. D can be negative or positive. So what happens if d is negative? Well, this integral at infinity goes slower than 1 over x, and that just means that the integral is finite. Likewise, if d is positive, then this starts blowing up at infinity. So it means we get a divergence. In fact, we call it a power law divergence. Okay, and then as you can tell, I left the gap in the middle. There's going to be a marginal case, and the marginal case will be when d is equal to 0. This means that this integral goes like dx over x, and that's a logarithmic divergence. Okay, so if you actually wanted to study the dependence on the cutoff, the logarithmic divergence is going to give you a divergence of the type log of the cutoff lambda divided by this scale, some momentum scale. And likewise, the power law divergence is that there's a very similar exercise you can do. It's going to give you lambda over p to the power, and that power is the superficial degree of divergence, hence the name. All right. So this is just some introductory notation. And in this lecture, again, following what we've done in the case of the IR, what we've done there is we've focused on a specific toy model theory in which things are easy to understand. Likewise, in this lecture, I'm going to consider a specific theory, which is the massless 5 to the 4 theory. Okay, so the reason to do that is that in this case, I can basically tell you the whole story in 1 hour. If we added the mass, it would take us a couple of hours to actually explain all of the aspects of running and so on. If we studied a more complicated theory, such as QCD or its sisters, then we would have to spend probably multiple lectures or even a whole course on renormalization. Okay, so this is just for simplicity. And let me remind you that in this theory, we have a single interaction vertex that typically the coupling is called minus I lambda. But for this lecture, since lambda already appeared here, and I don't want to confuse you, I'm just going to call the coupling G. And the minus sign is just conventional because G being positive corresponds to a healthy theory. Okay, and likewise, we're going to actually study this theory in 4 dimensions, or at least close to 4 dimensions, in which that theory is the most, is a good example for what I wanted to illustrate. And another aspect is that the power counting additionally simplifies because the vertex in here doesn't have any mass dimension. So what this means is that this numerator over there is always going to be some constant, g to some power. And what this means is that this degree here is always 0. Okay, so the power counting is extra simple. Okay, so let's actually, the idea behind this lecture is to understand the on-shell perspective on renormalization, basically. So to that end, what I'm going to start with is giving you the on-shell amplitude expanded in perturbation theory in this case. Okay, so you can probably do it in your sleep. At tree level, there's only 1 diagram in this theory. At 1 loop, there's going to be 3 diagrams, so-called bubbles. And then as you go to higher and higher loops, there's going to be more and more diagrams. So for example, at 2 loops, you're going to have this, plus these ones, maybe some bubble insertions or tadpole insertions. These ones, plus dot. And of course, as you go higher and higher in the loop degree, you get worse and worse contributions. So let me list a couple of them just for fun. This one, we have this non-planar diagram here. If you count carefully, this one has 3 loops, and so on and so on. Okay, so let's do a very simple exercise and try to compute the degree of divergence of all of these graphs in here. Okay, so let's start at tree level here. So at tree level, we're going to use this formula here with d is equal to 0. Well, the number of loops at tree level is 0, and the number of internal propagators is 0. So that means that this diagram here has d equals 0. let's look at any other diagram. Let's say this T-channel bubble in here, okay? So in this case, here D is equal to what? Well, it's going to be equal to space-time dimension 4 times 1 minus twice the number of internal edges, so that's 2. So that adds up to 0 as well. Let's do a more complicated example, maybe this final graph here. Okay, you can probably anticipate what's going to happen. So this one is 4 times 3, because we're at 3 loops. And then if you count the number of propagators, we have 1, 2, 3, 4, 5, 6. So that's twice 6. And that works out to be 0 as well. Okay, you can go home and you can work out the degrees of divergence of all of these graphs. In fact, you can spend an infinite number of time going to higher and higher loops. And, or you can just come up with a recursive argument, which would tell you that all the diagrams are, in this case, have degree of divergence 0, or as we call them, they're marginal. Okay, so what does it mean? It means that they're going to be integrals of this type that are going to give us more and more logarithms. But I actually have to emphasize something before we can actually write down some more concrete equations. And this is the idea of subdivergences. Okay, once we understand that, we'll be able to estimate the behavior of each diagram in perturbation theory. So you see what the exercise that we've done in here was rescaling all the loop momenta at the same rate all the way to infinity. But another thing that you could have done is you could have taken a subset of the loop momenta. For example, let's say this diagram has 3 loops. You could have rescaled one of the loop momenta to infinity or the other, or both of them at different rates and so on. And this is in fact how you can analyze the divergent structure of diagrams. Okay, so let's consider this example. Okay, so if I take the diagram, which is the whole thing, and I rescale F1 all the way to infinity, this is going to give me a single log because of the power counting. But on top of that, what I could have done is consider this subdiagram here, 2 loops. Okay, and this one is also marginal, so it's going to give me another log on top of that. Likewise, there's going to be, so this is the idea of nested divergences. Nested divergence means that the corresponding log or power law is going to multiply each other. Okay, so we can of course keep nesting. We can nest this one inside of the 2 loop and inside of the 3 loop. Okay. There's also the idea of overlapping divergences. So if you notice, for example, there's now a lot of lines here. If you look at this left so-called ice cream cone diagram, this one here, it actually overlaps with the right ice cream cone diagram at the bubble. Okay, so that's the idea of overlapping divergences. Okay. Whichever way you do it, the dominant effect is that there's 3 nested divergences, right? So each of them gives you a log of lambda. And then there's, as I mentioned, there's 3, the maximum number of nestings that you can have is 3. So they're going to multiply. They're going to give me a log to the 3rd power. And in fact, I know slightly more about this diagram. This diagram has the usual S, T, and U invariants. So let's call the energy coming here S. This diagram actually only depends on the S, only on the momentum that is being injected in here and flows out here. So that means that I even know what I'm supposed to insert here. I'm supposed to insert S, or strictly speaking, minus S. And for power, since S has the mass dimension 2, let me just insert the power counting in here. Okay, so you know that up to a number, which you have to do a specific computation, the leading divergence of this diagram is going to look like this, plus corrections. Okay, then many of you are more used to DIMREG, or dimensional regularization. So if you did that in DIMREG, you would find that each of the log factors would be replaced with 1/epsilon, and once again, they multiply each other. So this would give you, this specific diagram would, the leading order, give you 1/epsilon to the third power in DIMREG. All right. Do we have any questions at this stage? Oh, yeah. The question was why do we have the lambda squared? This is just because I'm not careful about the coefficient. So I could have written it as, lambda over square root of s or something like that. And you would just change this coefficient. Okay, any other questions? Yeah. Yeah, exactly. So the question was about the overlapping divergences. In this case, the issue would concern the subleading terms. In fact, it would not even consider, it would not, we would know that the expansion of this diagram is some number log to the third power, some number log to the second power, and then a single log, and then plus dot dot constant. The issue with the overlapping divergences would concern computing these numbers, actually. And this is something that is important at the higher orders in the running that I'm going to study later. In this case, they do not affect the leading term. Yeah. Okay, anything else? Okay, so in the next topic, we're going to discuss running of couplings from the on-shell perspective. Okay, so let me say I'm going to compute the 4-particle amplitude using this expansion in here. But as soon as I go to 1 loop or higher, I'm going to have a divergence. So that means I have to introduce my regulator, my cutoff. So let me emphasize that in here using kind of similar notation to what we've done in the last lectures. Now the meaning of lambda is the highest scale in the problem, and it's going to correspond to the UV cutoff, as I said before. Okay, so let me just kind of write down the general structure of what we expect to see, basically translating the pictures on that blackboard over there into equations. Okay, so the first thing is that we're going to have the tree-level contribution with a minus sign because of our conventions. Okay, and then at 1 loop, we're going to have g squared because there's always 2 vertices. And then what I'm going to write down next is kind of a version of this. The only thing that we know right now, without any kind of direct computation, is that all of these diagrams are going to behave as a log plus subleading terms. So let me just write that down without computations. Let me write it as this. Okay, and the terms that I'm ignoring here are for the G cube, so 2 loops and higher, I'm going to work at up to 1 loop order. And I'm also going to ignore, I'm going to explain what L means in a second. And I'm also going to ignore subleading terms in the cutoff. So p squared over lambda squared terms. Okay. Okay, so this L here, well, this L is just a collection of logarithms. This is just defined as these kind of factors. So I know that I have my 3 bubbles in what I'm going to call S, T, and U channel diagrams. It actually doesn't matter which one is which because everything is symmetric. Okay, so what I'm going to have is kind of a copy of this, except at the 1 loop, in which I have a log of lambda squared over minus S, minus T, and minus U. So you see, in principle, you can compute these coefficients, but what I'm actually going to tell you next is that if you're interested in renormalization, you actually don't have to do this explicit computation. We're going to find a shortcut. So that's going to be the goal of this lecture, and use more clever techniques based on unitarity to actually extract these coefficients without doing the whole computation at once. Okay, so one thing that I wanted to emphasize from the get-go is that here I chose the UV cutoff, but the choice of the UV cutoff is up to me. I could have chosen, that cutoff to be 1 GeV or 17 GeV. So here I'm, technically speaking, I've done a specific choice. So let me indicate that with an asterisk or a star. Let me put it everywhere. Here, here, here. Okay. And now you can ask, what happens if I actually try to change the cutoff? So see, the intuition is like the kind of intuition that you should have from your condensed matter courses. If you wanted to study, some properties of materials, you don't need to know about how the atoms inside of the materials interact. So that should tell you that at least at the low energies, the explicit value of the cutoff should not be important at all.
We expect by changing the cutoff, we expect A11 and A110 not change.
So the question was, if we change the cutoff, should we expect that the coefficients change? Is that right? The answer is no, and that's the magic of this kind of power counting. The sensitivity to the cutoff is entering through the logarithm. So the explicit coefficient here does not depend on that choice. Excellent. Any other questions? Okay, good. So now what we wanted to do is to change the cutoff. But notice actually the cutoff dependence is only through this function that I called L. So for that purpose, I can actually use the following identity, which you can easily verify. If I have an L at one cutoff, let me call it lambda star, and L at another cutoff, they actually only differ because of the properties of the logarithms. They only differ by minus 3 log of lambda over lambda. Okay, so what does it mean? Well, what I can start doing now is trying to rearrange the expression that we have here, just to try to fit it more into the structure of what we expect to see, except with a shifted cutoff. So one thing that I can do is rearrange it as follows. I'm going to write it as M4 with lambda star. I'm just going to copy the tree-level term, G star, so I haven't done anything yet. And then in the next step, I'm going to move this factor here, okay, into this bracket. So this is going to be 3 times G star squared. The minus sign is up front. And then this L is multiplying A11. And then I have the log from here. Okay. And then in the second line, I'm just going to collect the rest. So this is G squared. Now it's going to really take what I wanted to do is collect it so that it has the form of these factors, except with the other cutoff L lambda. Okay, and likewise, this is plus G cubed, and then P squared over the lambda squared. So I haven't actually done anything here. I've just reshuffled the terms around. This identity is the same as this identity here. It's the same amplitude. But now what I can do is actually impose this intuition that the physics at low energies should not depend on the choice of the cutoff at high energies, which originally, we'll would refer to it as the Wilsonian intuition. And I'm going to claim that my original amplitude, 4-point amplitude with the old cutoff, should actually equal to the amplitude at the new cutoff plus corrections of order p squared over lambda squared. So this is putting in equations what I said in words before, that the physics should stay the same up to some subleading corrections that are irrelevant at low energies. Okay, so let me write it down. Physics at low energies. Shouldn't depend on the UV cutoff. Okay, now the question is, can we actually realize this identity? And the answer is yes. But we have to give up one idea that was the central idea behind perturbation theory, which is the one that the couplings are constant. So you see, we can pull it off, provided that we identify this term in here as some new constant, new coupling constant. Let me call it G of lambda, that actually changes with the scale. So it differs from the original G star by these corrections if I go away from the original cutoff to any one. Okay? So if I make this identification, then I can actually write down that M4 with the new cutoff is going to be equal to minus G of lambda. It's just copying the first term. Then plus, well, naively, I would write down G star squared. But you see, to the order that I'm working with, G star squared is actually equal to G of lambda squared. I can just write it like this. And then in the brackets, I have my A11 L lambda plus the rest plus ... All right? Is the manipulation clear? Okay, so what we say is that this realization that the coupling constant is not actually constant, we say that the coupling runs with the cutoff in this case. And that realization is the central idea behind renormalization. All right, so now let me actually make this slightly more precise. This idea of running. And let me codify it. Yes? Yeah, so this is what I mentioned in words, that this term, you mean? Yeah, so this term got converted into this term, and that equality is correct up to the subleading corrections. So the idea is that I'm not going to do it in this lecture, but if you included more and more subleading corrections, this is always consistent, in which you can recycle the shift that was at the leading order. You can absorb it to subleading orders, and so on and so on. Yes? So there's a constant term, you're saying this one? This one, yes, this one indeed would be, I mean, the only thing that I'm saying is that G star squared, if you, sorry, maybe let me write it down. The only thing I'm saying is that this is true up to corrections of this order. Right. Thank you for clarification. Any other questions? Okay, so now what I'm going to do is I'm going to write the way that we typically think about the running, or how we calculate it, which is encoded in the Wilsonian beta function. Okay, so the Wilsonian beta function is going to be called beta subscript W of this coupling. Okay, I'm just going to define this as the new function that is going to be a total derivative of my G lambda with respect to lambda. So this beta function is just measuring the slope of the change. And one of the key ideas here is that that function itself does not depend on the lambda itself. So it has no lambda dependence. It only depends on the value, it's a function of the coupling. So that means that if I know the coupling at one scale, I can evolve it at others without knowing what kind of cutoff it refers to. That's the central idea. Okay, so I can actually use my identity from here, this one in here, and I can plug it in. And this gives me the value of the Wilsonian beta function up to one loop. Okay, so you see that the only lambda dependence that enters explicitly is through here. So I'm just going to compute the lambda of lambda, and this is going to give me, it's going to give me 6 times G lambda A11 plus higher order corrections. Okay, 6 is only because of the square of the lambda. Okay, excellent. So one thing that we found out in here is that the running of the coupling, so how coupling changes with the value of the cutoff, is actually sensitive to leading order only to this A11 coefficient. So this one, the coefficient of the leading logarithm, and in principle, the A10 at this order is completely irrelevant. So this already tells you that if you try to compute to one loop amplitude explicitly and then expand it in the large cutoff, you would be, in a sense, doing too much work. And what you want to do is actually extract only the leading term to minimize the effort. Okay? Maybe before going further, let me just mention, since I'm assuming many of you would have taken courses on the normalization and would have heard about beta functions. This one I'm calling the Wilsonian beta function. And the distinction, or the reason why I'm calling it Wilsonian, is that the running is performed with the cutoff scale, not with the physical scale at which I measure the couplings. And I'm actually going to come back to this towards the end of the lecture, and I'm going to tell you the difference between the Wilsonian philosophy to renormalization and the more traditional counterterm philosophy. All right? Okay, so next, what I'm going to do is I'm going to try to exploit as much as possible the fact that the running of the coupling is governed by this coefficient A11, and I will try to extract this coefficient in a clever way. And this is actually related to something that yesterday Yael Shatmi mentioned in her lectures, that there's a more clever way that exploits the connection between running and unitarity. So this is the next topic, running. Okay, so here the key idea is that we have this logarithm of some cutoff and some energy scale, say p squared. And one thing that you might know about logarithms is that logarithms may have a real or real and imaginary part depending on the sign of the argument. So let me write down one identity just to make this more explicit. I could have written it in this way, in which I have a positive argument plus factor of I pi whenever the p squared is positive. So I'm writing it as a step function in here. Okay, so the logarithm has the imaginary part with a factor of pi whenever the corresponding argument is time-like. So for our purposes, we're studying the 4-point amplitude. I could commit to a given scattering channel. Actually, it doesn't depend which scattering channel I'm going to choose. It's always the case that one of the Mandelstam invariants is positive. Let me call it S. And then the two remaining Mandelstam invariants are negative. Let me call them T and U. Okay, so you see that within this function L, which is still visible in here, out of the three logarithms, only one of them picks up the imaginary part. Okay, so let me use that fact. Okay, so if I wanted to compute the imaginary part, of the amplitude, okay, I know that the imaginary part is only going to come from one of the logs, say this one. Okay, so if I use my formula, then the imaginary part of the leading order is going to look like pi, and then g squared. Using my favorite identity, I'm going to trade it for g lambda squared, and then the coefficient, which is a11, plus corrections. Okay, you see, this is why we went through all this hassle. You see that the Wilsonian beta function was sensitive to A11, or was governed by A11, and the same A11 appears in the imaginary part of the amplitude. Okay, so that's a very interesting connection. Now we can actually exploit this connection by computing the imaginary part in a different way than a naive computation using Feynman diagrams. And in fact, what I'm going to do is use the optical theorem. Strictly speaking, so-called generalized optical theorem, which says that the imaginary part of the amplitude can be computed as a sum over cuts. How many of you have seen this statement before? All right, all of you are experts on amplitudes. So how would this work at one loop level? Well, I have the S, T, and U channel diagrams. Okay, and now to compute the imaginary part using optical theorem, what I have to do is cut it. Okay, so let me say this is the S channel. Okay, so I cut it in the S channel. So the way I can cut this diagram is like that. Yes? So I think the question was about a secret assumption that I made, which says that A10 doesn't have an imaginary part. Yeah, I didn't want to spend too much time on it. You can argue for that using similar ideas. The idea is that, yeah, as before, A10 is going to be a constant, and then using unitarity, you can also argue that it should not have an imaginary part. But I'm going to, for the purpose of this lecture, I'm just going to assume it. Great question. Any other questions? Yes? Yeah, exactly. So I'm going to assume that both A11 and A10 are real, which are true statements. Okay, so we're back to our cutting. Now we have to cut, we've cut the S channel diagram. Now we have to cut the T channel diagram. There's actually one way that I can try to do it, which is this cut. Likewise for the U channel diagram, I can try to cut it in this way. But this is actually not allowed, or technically speaking, it's allowed, but the cut turns out to be 0. And the reason for that is that this would have to involve a process which is unphysical. So I would cut it, when I cut it, I always have to put the intermediate particles to be forward and on shell. So forward time-like and on shell. And if you try to organize it using this diagram, it's never possible. So what this tells me, this is very much connected with the fact that S is time-like and T and E are space-like. So what this tells me is that these two contributions are actually 0. So the only non-zero contribution is this one. So this is the statement that we wanted to make when I said that, in principle, you don't need to compute the full amplitude at one loop. You just need a small part of it. This is basically codifying that statement. So in the next step, I'm just going to apply the identity to compute this cut. Okay, so if I wanted to be careful about it, there would be G squared lambda. If I compute the cut, there's going to be some normalization factors. I'm just copying it from a book. Okay, and then the cut tells me that what I have to do is I have to integrate the bubble integral, but instead of putting the propagators, I'm putting the on-shell delta functions. All right, this makes it very concrete. If I wanted to compute A11, the only thing that I have to compute is this integral. This integral is much, much simpler than doing the full bubble integral. So those of you who have suffered for this before would have known that. This one is quite easy to do. You go to some spherical coordinates, blah, blah, blah. And this is going to be some number. It's an important number. It turns out to be pi over 2. Okay, so that's homework. And it's important because it allows us to finally, by equating the second line and the final line, read off the A11. Okay, so A11 is equal to 1 over 32 pi squared. And what this also tells me is that the Wilsonian beta function, which is the additional factor of 6, is going to look like 3 times g squared over 16 pi squared at one loop order, so plus dot dot dot. Okay, so the thing, let me write it here before. This is entirely fixed by unitarity. Okay, So now that we've computed the beta function, we can have fun. See, at this stage, what you're left with is some differential equation in a single variable. First order, you can just solve it. Okay, so you can solve this differential equation, and it would tell you that g of lambda is equal to this. Okay, so in fact, I need to put a boundary condition, but now I know which boundary condition I'm supposed to put, right? Because the boundary condition is that the g at lambda star was my original g star that I defined to begin with, the original coupling. All right, so let me put this on the plot. Okay, so on the plot, you can study here the cutoff and here the coupling. Okay, there's going to be a special point somewhere here, in which case I have my special original, say, cutoff, also known as the subtraction point, with respect to which I just normalize how the plot looks like. And then from there, so you see if you plug in lambda is equal to lambda star, this just becomes log of 1, so this disappears, and we have g star, so that's how it looks like. This is the subtraction point. Okay, and then from there, there's some evolution that is governed by this equation, may kind of look something like this. And there's also one thing that you might notice about this. If you try to crank up the energy, the cutoff rather, to be very, very large, at some point, the value of this function here, this logarithm, is going to compete with 1. So what this means is that there's going to be a pole in this expansion, somewhere at the energy of lambda star with an exponential, which is 16 pi squared divided by 3 g star squared. And this is known as the Landau pole. So the Landau pole tells us that there's a limit to this perturbative expansion, and in fact, the running starts to break down at the exponentially high cutoff scales.
Landau pole removed if we add the higher order correction to the beta function.
The question is whether the Landau pole gets removed when we add higher order corrections. I believe the answer is no. It's going to wiggle a little bit. That's about it. Well, actually, we can discuss it over lunch or something, but there's a special thing about 5 to the 4 theory called triviality that is kind of related to this high cutoff behavior of the theory. Okay, let me skip that. Okay, so in the last 5 minutes, as I mentioned, this is the main message that I wanted to get across, that the running of the coupling is fixed by unitarity. So you can use your technology of the on-shell methods and computing cuts to actually understand running. Another thing that I guess I forgot to mention is that as the consequence of the generalized optical theorem, in this case, it was actually guaranteed that the imaginary part has to be positive. Okay, so it was no accident that we found this coefficient to be positive. Because we're computing the coupling, which is left-right symmetric, in a sense we can compute this in the forward limit. The optical theorem tells us that this was guaranteed to be positive, which told us that that this coupling has to be positive. This coefficient has to be positive, which in the end told us that the trajectory goes up, not down. So that's a consequence of unitarity. Okay, so in the last 5 minutes, I just wanted to explain some vocabulary and jargon that people use, and related to the type of renormalization that you would have seen in books on quantum field theory, perhaps. Okay, so I call them renormalization philosophies. So this is something that confused me a lot back when I was a student looking into those topics, because when we talk about renormalization, there's really two schools of thought. And one of them is the Wilsonian philosophy. So the Wilsonian philosophy is mostly used in the context of effective field theories and perhaps condensed matter physics. Okay? And it's this intuition that I can forget about the fine details of my system if I'm studying it at low energies. And I wanted to contrast that with the other philosophy, which is, I'm going to call it counterterm philosophy, which is what we usually use in particle physics computations. Right? So diagrammatically, what we've done in this lecture is that we had my energy scale, and originally I've put some cutoff, which I called lambda star. And what I said is that this is a cutoff, so I'm just going to ignore all the degrees of freedom that lie above that cutoff, right? Just don't touch it. Okay, and there was some physical scale somewhere down here, let's say. Let me call it mu for this purpose. And in that scale, we've defined our theory. And that theory was defined with my original coupling, which is G star, also known as G of lambda star. Right? And then what I've done in the next step is studied what happens if I take my original cutoff and I wiggle it a little bit to be higher or lower. So let's say a new one was lambda. Okay. And then there was some degrees of freedom that lied between my original cutoff scale and the new one that now are absorbed in my theory, right? So if I probe the theory at the same mass scale, now what I have to do is that effect gets readjusted into redefinition of the couplings. So this is what I call the new coupling, G lambda. And from this perspective, the reason why G runs is that there's new physics that I'm taking into account that is built by my effective parameter. Okay, so here I wanted to maybe write it down explicitly what I mean here. This lowercase scale is the physical scale, while this lambda is the cutoff scale. They should not be confused. Okay? So now let me try to contrast this approach with the more traditional counterterm approach. In this approach, we would do the following. We would still have our energy axis. We can still put a cutoff, lambda star. And then there would be some physical scale or renormalization scale, mu star. Okay, and the first step is the same. We just define our theory here with some G star, which is usually called the Baire coupling. Okay. So mechanically, to actually renormalize the theory using counterterms, it involves very similar, almost identical manipulations. Just the philosophy of how you interpret that computation is different. So that's the only thing that I wanted to emphasize. Okay, so in this case, what you do in the first step is that you say that you renormalize the coupling. So what this means is that at the same mass scale, mu star, you now defined a new coupling, G renormalized, that depends on the scale. Okay, and at the same time, you remove the cutoff. Okay, so when you remove the cutoff, there's going to be some divergences that appear. You just pretend you absorb it into the redefinition of the coupling, which now can be infinite. This is okay, couplings can be infinite. The reason is that the only thing that you can actually measure in, say, in an experiment, or Gedanken experiment at least, is the difference between couplings at different scales. So if there's some zero mode that just is infinite, it's fine, as long as the difference is finite. And this is the last step to parallel the step 1 and 2. Is going to be this one and the next one here, in which you compare the, instead of moving the cutoff, you move the physical scale, or the RG scale, from some mu star into a new mu. Once again, the cutoff is already removed. And then at this scale here, you compute it with renormalized coupling that runs. The only difference is that the running is now with the RG scale, not with the cutoff, like in the Wilsonian approach. Okay, so to make that concrete, let me call this the renormalization scale, or physical scale. And then cutoff is no longer relevant because it's always removed. Okay, so before moving forward, before kind of wrapping up, let me also, just to dispel any further confusion, these were the two renormalization philosophies. You also heard perhaps the terms regularization scheme. And also the renormalization scheme. It really sounds like a conspiracy that was meant to confuse all the graduate students that are all named almost the same. But they actually represent very distinct concepts. So each of the renormalization philosophies can be using a different regularization scheme, and you can also use different renormalization scheme. Regularization scheme is simply the choice of how you make your integrals, how you implement the cutoff. So I mentioned the dimreg as one of them. You can use dimreg here or here. You can use the hard cutoff. This is what we've done in this lecture. You can once again use it here or here. And then you can use more fancy techniques like Pauli-Villars, zeta function regularization, and things like that. Okay? And then finally, there's the thing called the renormalization scheme. And the typical names for them are the Onshel scheme and things like MS or MS bar scheme and others. And they're also called subtraction schemes. They have to do specifically with the fact of how you actually define the renormalized couplings in here. So basically, how many terms out of this limit are getting absorbed into the new renormalized couplings. All right, so I'm way out of time. So let me mention that if you wanted to learn more about it, please feel free to approach me after the talk, and I'm happy to explain how these differences work, and also how to extend these kind of relationships between RG and unitarity to higher orders. And tomorrow, what we're going to discuss is a very similar story in effective field theory, in which the coefficients in effective field theories can be also captured by constraints from unitarity. Okay, so thank you and see you tomorrow.
Any question?
Thank you. Then, if asymptotic freedom is due to the negative or positive the imaginary part?
Yes, so I think the question was about the asymptotic freedom and how it fits into this perspective. So as you know very well, the asymptotic freedom means that the running is in the other direction, so things become weaker, the coupling becomes weaker, and then it's actually a very useful exercise. How is the statement about the positivity of the imaginary part compatible with this change in sign of the strong coupling running? And what was special about the running in the 5 to the 4 theory, you see, was the fact that the 5 to the 4 theory is symmetric. So when I have the bubble, it's the left-right symmetric. So in this case, I have the optical theorem that tells me that so you see the important part in the optical theorem is that I can use the forward limit, meaning that the initial states are the same as the final states. If you try to compute it for the strong coupling, that is no longer the case. So even if you compute the cuts, they are not guaranteed to be positive. And in fact, this is what saves you from the running up. Instead, you run down. So that's how things are compatible. Excellent question.
Other question?
The question is whether the fixed points are the same in the two schemes, whether in the two philosophies, I'm assuming. Yeah, up to details, yes. The detail is how you interpret the result. But as I said, the math, especially one loop, it's almost like one-to-one. They would find the same result. Just the interpretation is slightly different if you remove the cutoff or you run the scale. But yeah.
Okay. If there's no more question, then let's thanks again. Yeah, we'll